So, what if the rules that govern one single tiny atom are the very same rules that build a conscious mind, and even the entire universe? Well, in this explainer, we're going to go on a journey, from the unbelievably small to the infinitely large, to find the hidden connections that tie everything together. Let's dive right in.
We're going to be exploring one central, just massive question. Is there some kind of fundamental rulebook that links the bizarre dance of quantum particles, the spark of consciousness inside our own heads, and the grand architecture of the universe itself? To even begin to answer that, we have to start at the absolute bottom, at the very foundation of reality. So yeah, our journey kicks off at the smallest scale you can possibly imagine, the quantum realm. This is the bedrock that everything else is built on, and it's a place where the rules we're all used to just break down and get really, really weird.
Now, you might think these quantum ideas sound strange, and you're right. But get this, even the physicists who discovered them found them deeply unsettling. This quote here shows that when Schrödinger came up with his new theory, his colleague Paul Dirac, one of the giants of physics, was totally against it. He was fine with the old theories. It just goes to show you how completely counterintuitive this new vision of reality really was.
Okay, so here's the crucial point, this massive shift in thinking. Classical physics, the world of Newton, it was deterministic. If you knew the position and speed of everything, you could predict the future perfectly. But quantum mechanics just threw that right out the window. It replaced it with probability. All of a sudden, the universe wasn't a perfect clock, it was more like a casino. And this famously bothered Albert Einstein, who argued that God does not play with dice. But you know what? So far, it really seems like the dice are all we've got.
All right, so the quantum world is fundamentally bizarre. It's based on chance. But here's the crazy paradox. We've actually learned to master those bizarre rules. We've used them to engineer the impossible, literally building our modern world atom by atom.
And this chart just illustrates that progress brilliantly. Think about the computer or the phone you're watching this on right now. Back in 1999, the transistors in a top-of-the-line NVIDIA graphics card were 220 nanometers wide. Today, they're getting ready to make them at just 3 nanometers. That is a shrink of over 70 times in only 25 years. That's not just an improvement, it's a complete redefinition of what's possible to build.
So how in the world did we pull off this incredible shrinking act? Well, we had to get really clever with the architecture. The old design, called FinFET, was kind of like a tall, skinny skyscraper, and it was starting to get wobbly, unstable. So engineers asked, hey, what if we just flip it sideways? And that's the whole idea behind the gate-all-around design, which stacks these stable horizontal sheets. The next step, CFET, is even more wild. When you run out of space on the ground, what do? You build up. We're now stacking transistors on top of each other, building chips in 3 dimensions.
And this is where it just gets truly mind-boggling. When you zoom in on the channel where the electricity is actually flowing in one of these new transistors, you're looking at a structure that is just 30 atoms thick. Not 30,000, not 300, 30. We are literally, and I mean literally, building our modern world one single atom at a time.
Building with atoms is one thing, but our mastery of the quantum world goes even further. What about handling something you absolutely cannot touch, like antimatter? If it touches regular matter, poof, they both annihilate. The solution is this incredible piece of engineering called a Penning trap. It's basically a container made of nothing. It's non-material. It just uses electric and magnetic fields to hold these antiparticles perfectly suspended in a vacuum. It's just amazing.
Okay, so we've learned to build with matter, and even contain its exact opposite. But this brings us to the ultimate arrangement of matter. What happens when it gets complex enough to think? We're shifting gears now, from the engineer to the emergent, to tackle the huge question of consciousness. Now this is a deeply provocative question. We usually just assume that life came first, right? And then, after billions of years of evolution, complex brains developed, and consciousness just kind of popped into existence. But what if that's completely backwards? What if some kind of feeling, some kind of motivation, had to exist before life could even get started?
Well, one pretty radical theory suggests consciousness isn't just a byproduct of a complex brain, but it's actually a fundamental quantum process. So deep inside our neurons, there are these tiny protein tubes called microtubules, and they seem to vibrate at quantum frequencies. But what's incredible is that these vibrations appear in this repeating, fractal-like pattern. The same rhythm echoes from the slow pace of our brainwaves all the way up to the insane buzz of individual molecules. It's almost like there's a hidden symphony connecting our thoughts directly to the quantum world.
And this leads to a truly wild idea, the quantum pleasure principle. What if the very first self-organizing molecules, these things called aromatic rings that formed in space and rained down on early Earth, what if they arranged themselves not randomly, but in ways that optimized for pleasurable feelings at a quantum level? The theory basically suggests that motivation, the drive towards pleasure and away from pain, isn't a product of evolution, but the actual engine of it. It's a mind-bending idea.
Okay, from the quantum world inside our own heads, let's now take the biggest leap we possibly can and zoom all the way out to the grand design of the entire cosmos. I mean, how do we even begin to wrap our heads around something so vast?
Well, one really powerful way is through a concept called projection theory. Imagine you're trying to understand a complex object, but all you can see is its shadow, right? If you look at the shadow from one angle, you get one shape. From another angle, you get a completely different one. But by combining all of these different 2D projections, you can actually reconstruct the 3D object. This is exactly how a CAT scan works, and it's a perfect metaphor for how we've built our picture of the universe.
And our projections have changed dramatically over time. Just about a century ago, in 1920, astronomers were actually arguing about whether everything we saw in the sky was inside our own Milky Way galaxy. Then, Edwin Hubble found a new way to measure cosmic distances and proved that the Andromeda Nebula was a whole other galaxy, millions of light years away. A few years later, he realized that all these distant galaxies were flying away from us, and the farther they were, the faster they were going. Our projection of a static, cozy universe was shattered. We suddenly lived in an expanding one.
Today, all of our combined projections give us this incredible picture, the cosmic web. The universe isn't just a random scattering of galaxies. Nope. Instead, they're organized into these immense filaments and sheets, surrounding vast, empty voids. And the whole thing is held together by an invisible scaffold of dark matter, whose gravity is what shapes everything we see.
Okay, we've journeyed from the infinitely small to the infinitely large. But this brings us to our final stop, the hard boundaries of reality itself, the very edge of what we can and maybe can't ever know.
Have you ever seen a message like this online? You're temporarily blocked. You were going too fast, you were misusing a feature, and now you're just cut off. It might seem totally random, but this is a surprisingly perfect metaphor for a fundamental limit of our cosmos. It's called the event horizon.
So this brings us to two cosmic horizons. The first one is the particle horizon. You can think of that as the boundary of our past. It's the farthest we can possibly see simply because light from anything beyond it hasn't had the 13.8 billion years to reach us yet. But the second one, the event horizon, that's the boundary of our future. See, the universe's expansion is accelerating. Galaxies beyond this point are now moving away from us faster than the speed of light. They aren't just invisible to us, they are gone forever. Any event happening there right now is permanently and forever cut off from us.
And yet, within this limited view we humans have an obsession with precision. This chart shows how the sources of our timekeeping errors have changed. With early mechanical clocks, almost all the error came from the device itself. Wear and tear, temperature changes. Then we started using the Earth's rotation as our clock, only to find that it was the source of error, because it's slowly slowing down. Today, with atomic clocks, both of those errors are basically zero. Our measurements are now so ridiculously precise, we're pushing right up against the fundamental limits of measuring the little slice of reality we can access.
And so, this brings us to our final connecting thought. Our journey began way down in the quantum realm, where reality is just a game of probability. And it ends here, at the edge of the cosmos, where our view is permanently walled off. So if the very foundation of our universe is uncertain, and our ability to even observe it is fundamentally incomplete, what does it truly mean to know reality? That's the ultimate question that connects the quantum all the way to the cosmos. Thanks for watching.